You'd expect such a tiny world to have solidified into an inactive ball of rock. But Mercury is geologically alive. It even appears to be shrinking.
On this month's programme, we'll be investigating Mercury's curious behaviour. And Pete Lawrence will be here to explain how you can watch the transit in safety.
So tonight, in all its glory, we give you Mercury, the most puzzling planet in the solar system.
Welcome to the Sky at Night.
At first glance, the thing that strikes you about Mercury is that it looks a lot like our moon. A bare, pale rock covered in craters. It's even a similar size. But in reality, Mercury is not at all like the moon. In fact, it's not like anywhere else in the solar system. Mercury has long been seen as an enigmatic planet, but it's difficult to observe because its orbit is so close to the Sun. So whenever we look at it, it's lost in the Sun's glare. Even so, with observations from Earth, we can map out Mercury's unusual orbit. Unsurprisingly, Mercury, being the closest planet to the Sun, has the shortest orbit. It takes just 88 days to go all the way round. It also has the most elliptical orbit of all the planets in the solar system. At its closest approach, it's just 46 million kilometres away from the Sun, and at its furthest, 70 million kilometres. Now that's unusual, but things get really weird when you take into account Mercury's rotation. Mercury rotates very slowly. It actually takes 59 Earth days for it to complete one revolution. But as it rotates, Mercury is also moving around its orbit. And the combination of rotation and orbit causes the Sun to move very slowly across the sky. So slowly, in fact, that from the planet's surface, a day, from sunrise to sunrise, actually lasts 2 complete orbits. So on Mercury, a day is twice as long as its year. That means that on the surface, daylight lasts the equivalent of 3 Earth months, and temperatures rise to around 450 Celsius. That's followed by 3 months of nighttime, where the temperatures plummet to minus 180. This temperature difference of over 600 degrees is the highest experienced anywhere in the solar system. That made it all the more surprising when astronomers at the Arecibo radio telescope bounced radar pulses off the planet. The signals that came back showed bright spots near the poles that bore the unmistakable signature of water ice. The shape of the ice deposits clearly showed that they were concealed in the depths of polar craters, the only areas on the planet that never receive any direct sunlight. That means that on this planet, 3 times closer to the Sun than Earth, you can still find water ice. That's pretty amazing.
But there's only so much we can tell by observing from Earth. To learn more about Mercury, we need spacecraft data. Only 2 missions have ever visited the planet. The first was Mariner 10 in 1974. Its camera only produced grainy pictures, but the other instruments it carried began to reveal major differences between Mercury and the other rocky planets. I've come to the Open University in Milton Keynes to talk to Mercury expert David Rothery.
when they see images of Mercury like this one, can't fail to be intrigued by it. It's got a wonderful landscape.
It's a beautiful image
Yeah.
as well, but we've only sent 2 spacecraft to Mercury compared to many that have been to Venus and Mars. Why is that? Why is Mercury being neglected?
Well, Mars and Venus are the low-hanging fruit. They're closer to the Earth, and at first sight, certainly they're more interesting. Mercury, when we first sent a probe by it, it's airless, it's heavily cratered, it's a little bit dull. Now we realise it's not dull at all. There's all kinds of things going on there.
Even that first mission, the Mariner mission that flew past, made some remarkable discoveries.
It did. It was equipped with a magnetometer to look at the interaction between the solar wind, the charged particles from the sun, and the planet's surface. But it found that the planet's generating its own magnetic field. It's like a scaled-down version of the Earth's magnetic field.
And that's surprising. For such a small planet to have a magnetic field is really, really unusual.
Absolutely. Mars, the Moon and Venus don't generate a magnetic field, but Mercury does. And it caught everybody by surprise. And thank goodness Mariner 10 carried this magnetometer.
But what does it tell us? What do we need to be able to generate this magnetic field?
Okay, well, some people say, well, iron in the core, you've got a core made of iron, it will be a magnet, but that doesn't work. It has to be fluid. You have to have an electrically conducting fluid churning around. So we think the outer part of Mercury's interior core is made of molten iron, and that's the explanation that holds for the Earth as well.
Well, that would make sense, apart from the fact that Mercury's such a small world. On Mars, for example, we think that there's no magnetic field because it's cooled down and there's no longer any fluid core.
Yeah, well, Mercury should be cooling down as well because it's got a large surface compared to its volume. It was probably quite hot to begin with, but there's also clearly some way of generating heat in the core to stop it having frozen, and also something to reduce the melting temperature of the outer part of the core. We think that is probably sulfur.
Mixed in with the iron.
Mixed in with the iron. There's got to be enough iron to make it an electrical conductor. So what we think is happening is iron is still today sinking inwards to join the frozen inner core of solid iron. And as the iron sinks inwards, it's turning gravitational energy into heat. And that's heating the outer part of the core, which is gradually becoming richer in sulfur, reducing its melting temperature and enabling it to churn round and generate a magnetic field.
So we know about one process that's happening inside Mercury. What do we know about the rest of its structure?
Well, we do know that the core must be very, very large compared to the size of the planet. Beyond the iron-rich inner core and outer core, you've got the rock. Most of the rock is what we call the mantle. There's a crust on the outside that's slightly chemically different. But this rocky outer part is much, much thinner on Mercury than it is on any of the other rocky planets.
It's the opposite of the Earth, where we have quite a thick mantle and a thin core. And so to me, this is one of the great mysteries of Mercury. Why do we have this large core surrounded by a thin mantle?
Absolutely.
Mariner had started to reveal Mercury's inner secrets, but we had to wait another 35 years for a really good look at Mercury's surface. That finally came in 2011, when NASA's Messenger probe started returning high-definition images like these. The team here in Milton Keynes are using these images to create detailed geological maps of Mercury, but they're also finding plenty more evidence of Mercury's strangeness. So Jack, if we can interrupt, what are you working on?
I'm making a geological map of a region on Mercury, this area you see here. I'm using data from NASA's Messenger satellite, planetary images mosaic together, and I'm interpreting the geological units I see at the surface.
And so what I see when I look at this globe of Mercury is craters, and I think that's what people think of. Like the moon, it's a grey body with a cratered surface.
Well, you're absolutely right. It is a heavily cratered surface in places. However, there is more to Mercury. For example, these lobate scarps that you see here. This one's called Carnegie rupees.
Okay, so that's this line running from top left to bottom right across the image.
Absolutely, yes. This is an escarpment in the landscape caused by faulting within the crust of Mercury.
So we see this kind of thing on Earth, these places where you have this sort of raised up area.
Yes, you see these things on Earth. On Earth we have plate tectonics, and because of the collisions of plates, we find them building mountains and making escarpments in the landscape, such as this one. However, there's no evidence to suggest that Mercury has multiple tectonic plates that move around and collide with each other. So instead, this is internal deformation within one plate. It's being drawn in from within.
So it's almost as if the whole planet is shrinking.
Yes, the planet is in a state of global contraction, and people have looked at the distribution of these lobate scarps over the planet and added up all their effects, and they calculate that perhaps the planet's lost as much as 7 kilometres of its planetary radius.
That's enormous. That's what? That's big. That's Everest-ish, isn't it? In size.
It's hard to imagine a planet shrinking, but Mercury demonstrates that it has.
So what's causing this? Why is there this shrinking?
As the planet loses heat, this causes a volume reduction, particularly because as the liquid part of Mercury's iron core freezes, that causes a volume reduction which pulls the crust in everywhere.
Okay, so it's quite a simple process. But Dave, if this isn't the only thing that's happening on the surface, if we look elsewhere, we can find evidence of other processes.
Oh, far from it. There's all kinds of things that have gone on Mercury. One thing that comes to mind is something that we didn't know about until Messenger got there, which is these areas called hollows. There's a view here that's about 20, 30 kilometres across, and it's showing an area of surface where the top 20 metres of material has just gone. It's been stripped away to leave that irregular area, and there's some smaller hollows nearby.
It looks a bit like mould or Swiss cheese or something like that.
Absolutely. How is it being removed? It's not falling into caverns, it's not being blown away in the wind, there's no wind. It's turning to vapour somehow and just being lost to space. So something in the surface is volatile enough to turn to vapour and just go.
And so what could that be?
It's a big problem, and we can't tell from this. It could be sulfur, could be chlorine. Is it driven by heat or charged particles breaking chemical bonds? But there is other evidence of a volatile richness in the planet, which was completely unexpected. Something this close to the sun ought not to be rich in volatiles.
Why not?
Well, close to the sun, you should be losing volatiles as you're trying to grow a planet because it's hot, and because Mercury has a large core, people thought it's had a violent birth. How do you get such a large core in a thin rocky area? Well, you blast the rock away, but that should be stripping away the volatiles as well. And yet Mercury has retained its volatiles and still got a large core. It doesn't fit.
And it's a world that's changing now. Some of these processes are still happening.
The hollow forming processes are still going on today. When you look at fields of hollows, you don't find impact craters superimposed. We think the hollows are still growing in some areas. And who'd have thought Mercury would be an active planet?
Well, it adds up to Mercury being a very exciting place. Absolutely. Thank you very much.
Pleasure.
One of the reasons that we knew so little about Mercury for so long was that it's difficult to observe from the Earth. But this week's transit will give everyone the chance to see this mysterious planet. And Pete is here to explain the best way to view the transit safely.
As planets go, Mercury isn't far away, only 48 million miles at closest approach. But it's surprisingly hard to observe, because being so close to the Sun, it is only ever visible for a short period just before sunrise or after sunset. But this week's transit is a great opportunity to see the planet during broad daylight. We won't get another chance as good as this until 2049.
Eclipse glasses are a great way to look at the sun safely, but unfortunately Mercury is just going to be too small to be able to be seen with the naked eye. It's about 1/155th the apparent size of the sun. So to see it at all, you're going to need something with a bit more power, say a telescope or a powerful pair of binoculars. But to be safe, these must be fitted with a certified solar safety filter. There are various filters available, but one of the easiest ways to achieve this is to get hold of an A4 sheet of solar safety film and then make your own filter, which slips on the front of the telescope just like that. You can point the telescope at the sun and you're good to go.
With the filter in place, you should get a view of the whole of the sun's disk, on which it's possible to make out small sunspots. This one is about the size that Mercury will appear during the transit. The transit will begin just after noon, with the sun high in the sky. You will see Mercury make first contact with the eastern edge of the sun and will then track southwest until the transit finishes at 7:42 in the evening.
If you don't have a filter, then there is another way to get a decent view of the sun, and that's to project it. Now, projection is only really suitable for small refracting or lens-based telescopes. But using a small refractor, if you point this directly at the sun with an eyepiece in the eyepiece holder, it's then possible to project an image of the sun onto a piece of white card, and it actually gives you a really good view. One final warning, if you're using this method, is to not keep the telescope pointed at the sun for too long a period. If you do, you run a risk of damaging the internal components of the telescope. If it's got plastic bits inside, for example, they may melt, and plastic eyepieces may melt as well. Also, be careful because the temperature just behind the eyepiece is really hot. I can demonstrate that with this little piece of black card. Look at that didn't take very long at all. Makes Bear Grylls look pretty pathetic, doesn't it? Hopefully on the day of the transit, the skies will be lovely and clear like they are today. But if the clouds do come in, the event is so long at 7.5 hours from beginning to end that we do stand at least a decent possibility of some clear breaks where we'll see something of it. Now, the end of the transit occurs with the sun just 9 degrees above the northwest horizon. So if you do intend to watch the entire event, then make sure you've got a clear view in that particular direction. So clear skies and good luck.
If you don't have the right equipment, there'll be lots of events happening all over the country, like here at the Open University, where you can watch the transit in the company of your local astronomers.
And if it does happen to be cloudy, like today, then ESA are streaming the transit live from space, using satellites that will get a great view whatever the weather. And we'll have details of that stream and the list of events on our website.
But transits are more than just rare and remarkable events. They also have significant scientific value.
We asked public astronomer Marek Kukula from the Royal Observatory Greenwich to investigate.
To understand the importance of transits, we need to go back to the 17th century, to the time just after the founding of the Royal Observatory.
This is what was known of the solar system in the second half of the 1600s. The 6 inner planets all orbiting around the Sun. The outer planets, of course, hadn't been discovered yet. It was a model we'd had since the time of Copernicus and Kepler. We knew the order of the planets, and we knew the shape of their orbits. But there was one thing about the solar system that we didn't know. We didn't know how big it was. Although the relative sizes of the orbits were understood, for instance, we knew that the Earth was 3 times further from the Sun than Mercury, the actual distances weren't known.
It was a solar system without scale.
And that's where this guy comes in. He's Edmund Halley. He'd later become Astronomer Royal himself, but in 1677 he was just an assistant astronomer here at the observatory in Greenwich. And he'd been sent to St Helena in the South Atlantic to observe the southern skies. While he was there, he watched a transit of Mercury, just like the one that's due this week. Watching Mercury crawl across the face of the Sun, Halley realised how a transit could be used to measure the size of the solar system.
Halley's breakthrough was to understand that if you viewed the transit from 2 widely spaced locations, thousands of miles apart, then you'll see the transit differently.
Viewed from here, south of the equator, the planet will appear here against the disk of the Sun. But viewed from north of the equator, the planet will appear further down on the Sun's disk. What Halley realised was that if you could measure the apparent separation between the points, the parallax, then you could work out the distance between the Earth and the Sun.
It was a calculation that required some fiendishly complicated geometry. But to produce an accurate figure, it also needed a number of extremely precise measurements to be made during the transit, including, most crucially, the exact time it takes for the planet to cross the Sun. But here Halley faced a problem. Mercury was so small and travelled so fast that it would be almost impossible to make the measurements required. A more suitable target was Venus, which appears both bigger and slower as it transits the Sun. But the next transit of Venus wasn't due for another 84 years. Halley knew he'd be long dead by then. So he laid down the gauntlet for future generations. Almost a century later, the world's astronomers rose to that challenge.
There were transits of Venus in 1761 and 1769, and expeditions were sent out all around the world to observe them. These expeditions were among the first great international scientific collaborations, and in many ways they were like the Large Hadron Collider or International Space Station of their day. The French, British and Austrians went to Siberia and northern Canada, where they had to brave polar bears and hostile locals. They went to the Indian and Pacific Oceans. Captain James Cook was sent to Tahiti in 1769. And these were major expeditions for the time, involving perilous sea voyages, sometimes lasting several years. There was one French expedition to Mexico from which only one person returned alive. And to make matters worse, during some of this time, France and Britain were at war, and special arrangements had to be made to give safe passage to scientists from each side. Once they'd arrived, each team had to spend weeks calculating their latitude and longitude. And this is data from Cook's voyage in 1769. You can see how detailed it is. They're even using the moons of Jupiter to calculate their longitude. And once they'd done that, they then had to hope for clear skies for the transit itself. The crucial measurement was to time how long it took Venus to cross the disk of the Sun to within a couple of seconds. And these are drawings by Captain Cook himself, and they perfectly illustrate a really crucial problem that they discovered. It's an optical illusion, the so-called black drop effect. And as Venus starts to cross the disk of the Sun, the disk of Venus appears to stretch out and blur, and that makes it very difficult to measure the precise time at which the transit begins.
The black drop effect made it impossible to record the length of the transit with the desired accuracy. But the data they did collect was enough for astronomers to start their calculations.
In 1771, the French astronomer Jérôme Lalande calculated a value for the astronomical unit, the distance between the Earth and the Sun, of 153 million kilometres, which is impressively within 2.5% of the modern value. Suddenly, the solar system had a scale.
That's why transits were important historically. But today, transits are still important in helping us understand our position in the universe, because of the role they play in showing how many other planets there are outside the solar system. Whenever a planet passes in front of the Sun, it blocks out a small but measurable amount of its light.
The same principle applies when we look at other stars. It's very, very difficult to observe their planets directly, but we can see the tiny drop in brightness as the planet passes in front of the star.
It's exactly this technique that the Kepler Space Telescope uses. It monitors 100,000 stars, looking for the telltale dip in luminance that indicates a transiting planet. By using this method, it has in the last 7 years detected nearly 6,000 possible exoplanets.
When you're watching a transit like the one this week, you should bear in mind a couple of things. One is that what you're watching is a clear example of the solar system in action, planets actually moving along their orbits in real time. But also what you're seeing isn't just a pleasing spectacle, because transits, perhaps more than any other phenomenon, have helped us to understand the scale and scope of our universe.
Mercury is undoubtedly a strange world. With its large iron core and its thin mantle, it's not like any of the rest of the family of rocky planets. So what happened in Mercury's formation to make it this way? Maggie has been talking to planetary scientist Craig Agnor to discuss the latest ideas.
Craig, can you describe to me the old theory of the formation of Mercury?
One of the initial ideas was that Mercury's mantle was removed through a giant impact. And the initial modeling of this suggested a smaller object, maybe a third the mass of Mercury, smashed in at very high velocity, vaporized the mantle, blasted off into space. And this would have predicted a very hot but iron-rich planet.
Okay, so an iron-rich planet, so a large core and a thin mantle. So that does tie in with what we see of Mercury.
That's exactly right. The problem is that recent spacecraft data have shown that Mercury's mantle retains a significant inventory of volatiles that wouldn't have survived the extreme heating of this initial scenario.
Okay, because yeah, they would have just been sort of blown off into space with the temperature.
That's right.
Okay, so there's a challenge there.
That's right. So you have to look at the different types of giant impacts that occur during planet formation. One of the new ideas about this origin of Mercury is that maybe Mercury hit a larger object at slower velocity, and this collision may be able to remove the mantle without the extreme heating of the earlier scenario.
Okay, so we keep the volatiles.
Exactly
Wonderful.
right. And so what we see in this animation here is kind of a proto-Mercury and a proto-Venus on crossing orbits that will eventually result in a giant impact.
Oh, I see. So the impact was actually between Venus and Mercury.
Right.
So what actually happens during impact?
Well, the way we study this is through computer simulations. And you can model a planet in this simulation from Arizona State by Eric Aspog and Andreas Reufer as an iron core shown in blue. The rocky mantles are shown in red or orange. This type of collision is called a hit-and-run collision, where the two objects slam into each other, they shear off a portion of their mantles, and they leave the scene of the crime. The impact happens at a modest velocity, and so this is quite a bit more gentle than the smaller high-velocity impact collisions.
Okay, so this could actually explain sort of the core, the mantle, but the volatiles as well.
That's right.
So in this scenario, what happens to Venus?
Well, a part of the proto-Mercury's mantle may have been deposited onto Venus, and that may help to explain why Venus actually has a little bit more mantle material relative to the size of its core than the Earth.
So this theory is looking pretty good now, because we've got this collision, we've got Mercury left with a large iron core and a thin mantle, we've got Venus with an extra mantle, which is what we actually see in reality. So it does seem to stand up. So, okay, what happens next?
Well, yeah, it's not the end of the story, because its orbit continues to evolve. And over the next 5 billion years, there's about a 1% chance that its orbit can become so eccentric that it again crosses the orbit of Venus. It can suffer giant impacts with Venus or Earth, or it may collide with the Sun.
Gosh, a 1% probability is quite high, really.
Yeah.
That in a solar system could change radically.
That's right.
So it's not as static as I take for granted.
No, the solar system is an amazingly dynamic place.
Thanks very much.
Thank you.
Mercury was the least interesting of planets, but the more you find out about it, the more fascinating it is.
I was particularly interested in the fact that the formation of Mercury tells us more about the dynamics of the early solar system.
Well, that's all we've got time for this month, but if you're going to watch the transit tomorrow, good luck. And if you're watching us on repeat, I hope it was clear.
That's it for this month, but do check out the website where we've got Pete's Star Guide. And in the meantime, get outside and get looking up, but never directly at the sun.
Good night.